Good morning, everybody. In this particular problem, we're going to find out the electric field due to 2-point charges. So we have one charge Q1 and we have another charge Q2, and we are interested in finding out the electric field at point P. So the electric field has the same direction as the direction of the force. So this is positive charge, this is negative charge, and we have the test positive charge here, P, or we have a point P. So the electric field due to the positive charge is away from the charge. So this one is radiating outwards. And always remember, the electric field due to the negative charge is always towards the charge. So this is towards the charge. Okay. For the positive charge, it's away, and for the negative charge, it's towards. So we have the electric field along this direction, and we have the electric field along this direction. So electric field is a vector quantity. So when you have two vectors, then you have to find the resultant of the two vectors by using the vector addition approach. So the way I will solve this problem is, first I'll find out E1 and E2. Let's do that. How I'm going to find out the electric field? So the electric field is given by K times charge over R squared. Okay, and the K is a constant. This value is given in any book. So the magnitude of K is 8.99 to the 10 to the 9 Newton meter square over Coulomb square. And this charge Q1 is the magnitude of this charge. It's given here, right here, 7 microcoulomb. And then just plug in this value, 7 microcoulomb. And remember, what is the 1 microcoulomb? 1 microcoulomb is 1 into 10 to the minus 6 coulomb. Okay? So once you plug that, you will get this magnitude, 3.9 10 to the 5 Newton per coulomb. And we'll talk about the direction later on. Same way, I'm going to calculate the E2, which is given by K Q2 over R squared. Again, the K is 8.99, 10 to the 9, and the magnitude Q2 is 5 microcoulomb, negative 5 microcoulomb, and the magnitude is same, 5 microcoulomb. And the distance now here, what is this distance? R is the distance between the point and the charge. So this is given 0.40 meter, and this is given 0.3 meter. So you know this distance and you know distance. How are you going to find this distance? This is just use the Pythagoras theorem. So you have to take a square, 0.4 square, 0.43 square, and take a square root. So this distance is 0.5 meter. Okay. If you know this distance, you know this distance. How are you going to find this distance? A square and add the square of this distance and take the square root. That's how you're going to do it, and which is 0.5 meter. So in this case, the distance is 0.5 meter. So I just what I did, I just plug in all the distance here, 0.5 meter, and solve it. So this value is equal to 1.8 times 10 to the 5 meter per coulomb. Now, once you have all this magnitude, you see E2 is not is somewhere in between the x-axis and the y-axis. I'm going to resolve this one into the two components. The one is, let's say this angle is theta. If this is angle theta, this angle is also theta. So cosine theta in this triangle is b over h, which is 0.3 over 0.5. And the sine theta is p over h, which is 0.4 divided by 0.5. So sine theta is 0.4 over 0.5. So now E2 has two components, one along the x-axis and the one along the y-axis. Along the x-axis, this component is E2 times cosine theta, and along the y-axis, this is E2y times sine theta. So this has two components. The one is E2 along the x-axis is E2 cosine theta, and along the y-axis this is E2 sine theta. So what I did, I just plug in the values, E2 value. We already have calculated E2, and cosine theta is 0.3 over point h. Just plug in the numbers and get this value. And the same way, I calculated E2y, which is E2 sine theta, and the sine theta is 0.4 over 0.5, and I solve this equation. Okay, so I know now what I see here, the total electric field has only one value along the x-axis, but along the y-axis I have two values, E1 and E2y. So what is the net component along the y-axis? You see here, we have two. Along the positive axis I have E1, and along the negative y-axis I have E2y. So total electric field along the y direction is EY is equal to E1 minus E2y. So this gives the total electric field along the y direction. Okay, so now, so what is the total electric field then? I'm just erasing this one. Okay, so along the x-axis, so we have total electric field is now given by, you remember we have only one component along the x-axis, so the E2x is given by, so E2x, which is 1.1 to 10 to the 5. And we have along the y-axis, what is the total electric field? This is the total electric field, 2.5 plus 2.5, 10 to the 5th. This is Newton per Coulomb. And this is along x-axis, and this is along y-axis. Okay? So this is the total electric field, and I'm just putting a vector sign here. And now the magnitude. The magnitude of this field is given by 1.1, this is the square, plus 2.5 square. So you have to take, when you calculate the magnitude, you have to take the x component and you have to take the y component, square them and take the square root. And the value you will get, you can write down the value here, is 2.7, 10 to the 5th Newton per Coulomb. And the angle now. The angle is given by, how do you find, if you know a vector, how do you find the angle? In order to find the angle, you have to take the tangent inverse, EY, which is 2.5, divided by the x component, 1.1. So when you find the angle, you have to take the y component and you have to take the x component. So when you do the math, you get the 27 degrees. So what is this angle means here? So we have taken the, so we have the two components. One is E2x, and the total force, the total electric field, let me draw here. So we have the vectors here, E2x, and we have the net E, this is E2x, or EX, or this is EY. If you draw a parallelogram, so this angle is phi. Okay, and remember this is E total electric field, and this is total electric field along y direction. So this angle is 27 degrees. Oh no, so this is my bad. This angle is 66 degrees. Okay,